Hi, I'm Dr. Matthew Michal. I'm a lecturer of mathematics at NJIT here in Newark, New Jersey. These videos are talking about differential equations, specifically from the book, 10th edition of Boyce and Deprimus book on differential equations. I'm trying to discuss and work through some of the examples and techniques as well as some of the information. This one's going to be kind of abstract. Talking about what do I think when I read these things. Okay, so the last section, or I guess for you, last section, we were talking about just general finding. We talked about the characteristic equation and the like. So this section is more about why did it work? How do I know that that's safe and the like? So what we're going to discuss is what does it make a solution, a general solution, and what makes a fundamental solution. So we're going to be looking for solutions on specific intervals. Most of the time we don't really talk about it, but we are wanting to consider when does a solution work? How long is that interval solution? Is it infinite? Is it finite? Is it somewhere between? A lot of times you'll see in this lecture and later on, I might use what's known as a differential operator. It's the thing that acts upon a function that plugs it into that differential equation. So remember, we were looking at differential equations of the type y double prime plus py prime plus qy. Remember, I said we oftentimes write it in lowercase. This means I've plugged in the function y into this differential equation. Notice I don't have a forcing term or equals to 0 on the right-hand side. I'm just saying, hey, look, here's this function. Okay, so for example, let's say I have a p function of t squared and a q function of e to the 2t. If I plug in the function sine of t, the linear operator of sine of t is negative sine t plus t squared cosine t plus 2e to the 2t sine of t. Does it mean anything? By itself. It can be useful, but in and of itself it doesn't necessarily mean anything. Frequently, though, we will want to look for, remember, a solution is going to be the case that when I plug it in the linear operator, it will equal to 0, at least for the homogeneous case. And it will fit those particular initial conditions. And what we're really looking for is that when I find those y solutions, that they are not only a solution, but a unique solution. And I also want to know the different characteristics. What's the form, or what's the structure, and what kind of things that I need to be considering. So theorem 3.2.1 is the existence and uniqueness. So taking a look at this system right here, if I assume that p, q, and g are functions which are continuous on some open interval around my initial conditions, then I will have a unique solution. Not only does the solution exist, but it will be the only solution. That's why we call it existence and uniqueness, because not only does it exist, it is the only useful. It is the only one that it works. Also, look at the note down below. Just because there is a solution, that doesn't mean that you're going to be able to write it down in any useful manner. See, while this theorem says that a solution to the initial value problem above exists, it is often not possible to write down a useful expression for the solution. So, I don't know if I would say it is often, but it is possible. It is a possibility that there might not be a useful expression for the solution. It could just be too disgusting. Okay, so let's look at this, right? So in order to make this differential equation above work in the theorem 3.2.1 form, is I have to make sure that this front term, there's my cursor, this term can't exist, right? There can't be anything in front of the y double prime. So by dividing by this front term, I get p term of t over this. Notice they both have a t, so the t can't stop, and I get 1 over t minus 3. The second case is a minus t plus 3, so I get a negative t over 3 divided by t times t minus 3. Now note, at t is equal to 0 and at t is equal to 3, I end up getting P and Q being discontinuous. There is an infinite discontinuity. T is equal to 0 because of this, and t is equal to 3 because of this. Notice that's why my initial conditions aren't at t is equal to 0. So, my initial condition, I now have this place. I have a discontinuity at 0 and at 3. But between 0 and 3, I'm good. Before 0, I'm good. And after 3, I'm good. So I have 3 possible realms of solution. So what I then look for is, where is my initial condition? Is it between the two? Is it before 0? Or is it after 3? And since it's between them, I could say that the longest interval of solution is 0 to 3 for this initial condition. Note in this case, it took me a half second to realize what the point they're trying to make. Take a look at the initial conditions. We have a function which has a starting off point at 0, the 0 slope. And in fact, if we go beyond that, if we just say y is equal to 0, that would indeed work. And the second derivative of 0 is 0. First derivative of 0 is 0. The function itself is 0. So 0 is equal to 0. It is a solution. Here's the thing. As long as P and Q are both continuous, Theorem 3.2.1 says, remember, it has a solution. We already found one, y is equal to 0, and it's unique. So this implies that regardless of P and Q, as long as P and Q are continuous, this solution will always have a solution of 0. It is a unique solution. The theorem of superposition. So for those of you who have taken physics classes before, you've seen this before. This is the idea of constructive and destructive interference. What it turns out to be is that our solutions are two waveforms, two functions that are going to be interacting. And what it turns out to be is that the solutions of this differential equation is going to be a linear combination. So it's a combination, so it's adding. Linear because it's first order, right? y1 and y2, not y1 squared or something. It's a combination of them. And so we need to be able to have some form of checking to make sure that this is the only way of writing it. We need to make sure that there's no copies, make sure that there's no overlap of information. And so in order to determine that these two are actually unique and that they're different, we need a new form. We need a way to easily check this. And that's why we use, notice at the bottom, the Wronskian determinant. So if y1 and y2 are solutions to this equation, we know by definition if they are distinct from each other, then that linear combination that we see in the second bullet point should be the solution to the equation, which means that my C1 and C2 should be solvable, right, using those initial conditions. Right, so plugging in those T0 values, that is technically a system of equations. And so C1 and C2 become those ugly looking things, but notice in the denominator for both of those terms, they're the same thing. That denominator, the thing saying, hey, look, I'm wanting to divide by something. If that term in the bottom, known as the determinant that you learned about in Calc 3, if that determinant is 0, that means C1 and C2 isn't possible to solve for, no matter what your initial conditions are. That term is known as the Wronskian determinant. Frequently, that's all we really need to check for. I mean, that formula for C1 and C2 usually isn't worth it, but the Wronskian is. So Wronskian is going to be something that checks to see, is this solution possible? Does this work? Because I don't want the denominator to equal to 0. So that check will be sufficient to see if y1 and y2 are distinct enough to get all the information from my initial conditions. The Wronskian is calculated as y1 times y2 prime minus y1 prime times y2. And if the Wronskian is not 0 at my initial condition, then the solution will be unique, right? Remember we talked about uniqueness? We will have a solution. It will be unique, and it'll be formed in the solution will be y is equal to c1 y1 plus c2 y2 on an open interval around my initial condition. So remember this, for example, from last time, we had a y1 which is e to the negative 2t and a y2 which is e to the negative 3t. They were solutions to this differential equation. Now we assumed they were the only ones, that they only worked. But take a look at the Wronskian. We have y1 which is e to the negative 2. We have a y2 which is negative 2 e to the negative 2t. y2 which is e to the negative 3t. And a y2 prime which is negative 3. This came down. E to the negative 3t. Multiplying these across like so, I'm going to get negative 3 e to the, well, negative 2 minus 3 is negative 5. And cross here, I get negative 2 e to the negative 5t as well. So this minus this, or negative 3 e to the negative 5t plus 2 e to the negative 5t gives me a negative e to the negative 5t. Now, if you take a look and you plot this, or if you just remember, you'll know that exponential functions never equal to 0. It approaches 0, but it never equals to 0. This means the Wronskian is never 0, which means that your solutions will work over the whole domain, the whole real numbers. And so that these solutions, y1 and y2, are indeed the correct ones. And we can write our solutions as c1 e to the negative 2t plus c2 e to the negative 3t every single time for this differential equation. And so, because of that, when it passes that Wronskian test, we go from a general solution, just c1 y1 plus c2 y2, that's a general solution, to a fundamental set of solutions when it does pass that Wronskian. So the general solutions, the form per se, fundamental set of solutions usually refers to the y1 and y2 separately. But we can only say that if the Wronskian is non-zero, at least at the initial condition. Notice that assuming that we get real and distinct roots, this will work every single time. So as long as we notice exponentials that have different roots, it will always work. So as long as we have real and distinct roots, it works every single time. Notice this even works when R1 and R2 are imaginary or complex. Nowhere did we say that this was real. All we said that they were different. As long as they're different, this will work. So let's look at this differential equation. Okay, so let's say that the solutions to this differential equation, because we're not ready to actually solve it yet, it's not exponential, polynomial solutions are harder. So let's say that these are solutions. And if you plug it in, it should indeed work. Notice we plugged the first y1 in. And then notice below we plug in y2. We do end up getting that the solutions, the differential equation, does equal to 0 like we want it to. Pause now if you want to take a second to look at that. But using the Wronskian, we can check to see if it works everywhere. Okay, so we have y1, y2, y1 prime, y2 prime. Cross multiply and subtract. We're going to get negative 3 halves t to negative 3 halves. So as long as t is greater than 0, because at 0 bad things happen, as long as the Wronskian is not 0, it works. It's non-zero. Technically, I guess it's never equal to 0, but bad things would happen. We don't want that either. So we get a solution, a fundamental set of solutions for the differential equation, where y1 is the square root of t, and y2 is 1 over t. Now, theorem 3.2.5 looks really useful, but be careful with it. It is really useful, but it isn't, for the most part, you might not necessarily want to use it. This becomes really useful if we want to focus in on and make C1 equal to my Y naught and my C2 equal to my Y naught prime. It allows me to say that my new Y1 and my new Y2 will focus in on what conditions we might have. So in this differential equation that we've been finding before, Y double prime plus P of T Y prime plus Q of T Y is equal to 0. I'm going to get two solutions, Y1 and Y2, naturally, from this, finding my R values and whatnot. Then I can redistribute a Y1 and a Y2 by solving the conditions where Y1 will be focusing in on the initial position, which has a 0 initial slope. And the Y2 will do the opposite, solve for the initial slope, but not the initial position. This allows me to have a C1 value and C2 value that are easily manipulated. So if you're solving a lot of, if you're having the same differential equation that you're moving around your initial conditions, this theorem is really useful to say, hey, look, I modified my initial position, so just modify C1. Hey, look, I modified this slope, I'm just going to modify C2. That's what this is really useful for. So let's take a look again at this differential equation, right? We've seen this before in the last section. Y double prime minus y is equal to 0. And we're going to say our initial time is 0. Easy, good one. Last time we talked about how the two solutions are e to the t and e to the negative t. So this theorem, like I said before, will allow us to solve for systems to create a new set of solutions. In this case, we're going to call it y3 and y4. My y3 will be easily usable describing initial conditions. My y4 is going to focus on initial slopes. Hence, the initial condition of 1 here and 0 here for y3, and 0 initial position and initial slope here of 1. So solving this, working through this, so C1, C2, and D1 and D2, I can solve for these conditions. So y3 ends up becoming 1/2 e to the t plus 1/2 e to the negative t. And that's the hyperbolic cosine function. And y4 becomes the hyperbolic sine function when solved for. Now this Wronskian is also non-zero. It's by definition equal to 1 due to a hyperbolic Pythagorean trig identity. Say that 5 times fast. This means that it itself is its own fundamental set of solutions. Whereas e to the t and e to the negative t is a fundamental set of solutions, so is cosh and sinh. But this would be a nice way to switch initial conditions around. Hence why this is useful. So notice both of them form fundamental sets of solutions. So if you don't like your original set of solutions, this theorem will allow you to choose a different one. This also shows you that there are more than one set of solutions that could be useful. So always pick the one that is most useful for what you're wanting to do. I'll talk about this more when we get to repeated roots, but Abel's theorem says, hey, look, I'm wanting to look for conditions. I'm wanting to look for these fundamental set of solutions. Abel's theorem actually works out the fact that if I know what P of t is, and it's in the correct standardized form, I can predict what the Wronskian is going to look like before I even calculate my y1 and y2. It can be useful in multiple cases, especially when we're solving for a repeated root problem. But if I know what P of t is, notice this should look very familiar from integrating factors. The Wronskian will always equal to some constant, which we might not be able to ever determine, e to the negative integral of P of t dt. So depending on my particular cases, I can predict what it's going to look like. So take a look at this one we did earlier, right? We talked about the solutions y1 and y2, where y1 was t to the square root of t, and y2 was 1 over t for that differential equation that we see here. And we calculated its Wronskian as negative 3 over 2 square root of t cubed. But if we standardize the form first, get 3 over 2t, and plug it into Abel's theorem, notice we will get a very familiar looking form. Because the integral of negative 3 over 2t, that's negative 3 halves natural log of t. Move the negative 3 halves above to the t, I get c t to the 3 halves power, because e and natural log cancel each other out. They're inverse functions. So notice in this case, c is negative 3 halves. But notice Abel's theorem was able to predict the Wronskian's value and predict where the difficulties would lie. So what t-values would not have solutions. And that's before I could even determine what these solutions were. So notice that for these solutions, for this differential equation, if I had not told you that the solution form was square root of t and t to the t inverse, you might not know what the solutions are. But using Abel's theorem, you would be able to predict that the solution would never work at t is equal to 0. This is incredibly useful. Okay, so what do we learn from this? We know how to find fundamental sets of solutions based on when are P and Q continuous. And on those domains, that's going to be where we're going to find our solutions. 2, we can determine when fundamental sets of solutions are based on when the Wronskian is ever equal to 0 or not. 3, that this indeed is going to always be our functional form due to that uniqueness in existence formula, right? Uniqueness in existence theorem. So once we find our y1 and y2, if it is a fundamental set of solutions, it's safe. That is the only answer. Have a nice day.